Good morning, good afternoon, and good evening, everyone. So today we're going to be going over some more exercises on partial derivatives. Right, let's get started. So for example 5, we're being asked to find the partial derivative of my z, so my output, with respect to x, as well as with respect to y. Okay. But the problem here is z is defined implicitly. So it's not an explicit function. Right? So let's see what that looks like. We have x cubed plus y cubed plus z cubed is, oh, my bad, plus 6xyz plus 4 equals 0, right? And once we find those partial derivatives, we want to evaluate them. So we want to evaluate these partial derivatives at a particular point in our quadric surface, which is -1, 1, and 2. And so how do we do this? We have to differentiate implicitly, right? So the idea is we first have to treat y as a constant and z as a function of x. So that's what we have to do. And so let's go through each term one by one. We take the derivative of x cubed. So let me just say implicit differentiation. So the idea of implicit differentiation, if we took calculus 1, is we have to differentiate both sides of the equation. And here I'm saying with respect to x. So here x is a variable, y is a constant or fixed number, and z is a function. So if we differentiate x cubed, well, we get 3x squared. Y cubed, that's a 0, so that's gone. Z cubed, well, that's a function, right? So we also do the same thing. 3z squared, and then we chain rule this thing, right? Actually, we don't chain rule it. Huh. Yeah, we just treat it with like a function. So we're gonna add this. Okay. Then here's 6xyz. Well, we just take the derivative of x, right? So it's gonna be a 1. So we have 6yz. Um, Actually, let me do this. 6xyz. So what's confusing about this is that we have a couple of stuff. Here we treat 6y as numbers. X and z are functions, or z is a function, x is a variable. Um, and so what happens here? Well, here we treat them like so. So let's do a product rule. Then I add here, what does this become? This becomes 1. So here I have xz. Then I add 6y. What's the derivative of xz? So we do the thing again. So it's really all about feeling these pieces or getting into these pieces. So this is 1. So I have z here. Then I have x here. Here I treat it as a function, right? So how would that look like? Well, I just take its partial. Right? And so here I have, well, yeah. And so here I basically have this that's partial, right? And then from there, well, now I have xz, 6yz, 6xy, or not the partial, there. So then I multiplied my 6y to both terms. And then that's my okay, I hope I got that one. Six, wait a minute. 3z. Where in the world did I get? Oh, so it's here. Okay. And then, yeah, okay, yeah, okay. Then I do 6xyz. Okay. So let me see. Uh, yeah, and then here we should get, that's funny. What do I do about the z here, the xz here? Because in uh my solution, it doesn't work that way. 6yz, 6xy. Um, okay, cool. Yeah, because I did a product wheel here. Or maybe I should have done it somewhere else. No, but here I just treat these as a number. That's the thing. And then I would get this. Since 6y is just, oh, 6y is a 0. This is 0, so this is completely gone. There we go. That's why I was so lost. 'Cause I was looking at the textbook. I don't know where I got wrong. Okay, but now I know. Yeah. And then we have 6xy, my partial. Okay. And this should give me 0, right? Well, obviously. Derivative of 0 is 0. Because there's no change in 0. That's why. Okay, so that's done. And then from here, what do we do? Well, now we basically solve it for our partial, right? So we solve for this thing. So how do we do that? Well, in algebra, we would just put them all in one side, right? So if we want to put them all in one side, I would say 3z squared, then my partial here, then I add, then my partial. Then this is equal to, I don't know, negative of everything. Because here I want to put them all in one side. That's it. Yeah, I have 4 terms. Then from there, I can factor out some stuff here. I could factor this out. Here's the thing about this notation is that you can treat it like a number. And then from there, you can do some stuff to isolate. Okay, it should be z. Well, okay. And then from there, could I simplify maybe? Yes, I think I could simplify. Because the textbook did not give a complete solution. So I was weird. That was weird. Yeah, here I'm just completing it, the solution. I can factor out maybe factor out the negative here. Just put out the front and make this a plus. And I could factor out a 3. So I get something like x squared plus 2yz. And I divide it by z squared plus 2xy. Yeah, then that's my answer. And similarly, we can do the same for y, right? So let me just do it. So here now we treat x as a constant and y as a variable. And so x cubed acts as a constant, that's 0. Y cubed, that's 3y squared. I think that was a plus after. Z cubed, z is a function. So we basically do the same thing. We differentiate our function and we get its partial with respect to y. And then we have 6xyz. So that one's the most confusing part. I have to dissect what this is. 6x here, I can treat it like that because that's a constant. And so let me do a product rule. And this one becomes a 0. So everything here is taken out. 6x here, well, 6x stays as 6x. Yz, on the other hand, now we can do another product rule again. The derivative of y is 1, right? So this is 1. So I have z. I have z plus, here I have y. And then here I have my partial, right? Okay, so what is this? Yeah, now we just plug in what we know. And there we have it. 6xz plus 6xy. There we go. That's it. And I'm pretty sure I add them, right? Yeah, I add them. Okay, so let me just quickly add these guys. 6xy plus, or no, not 6xy. 6xz, and then 6xy, then my partial with respect to y, and I should get something. Yeah, and that's how implicit differentiation works. And then from here, we can just isolate. So we get 3z squared. So I'm putting all of the terms that have partials in one side, just like the one I did in the previous one. Why? Because I can. Yeah. Did I miss something? I think I missed something. I have a 4, which just becomes a 0, and I have a 0, which is a 0. Oh, I missed the 0. Oops. Okay. So here I keep this in the left-hand side. I put my other terms without the partials in the other side. This is minus. Okay. And then I can factor out my partial here. Right? Then I can bring it down here. Okay, I hope I didn't mess up my... Okay, see if I got my answer. Yeah. Okay, yeah. Then I just factor out my negative and my 3. So here I get y squared. Add to 2xz, and I divide that by z squared plus 2xy. And there we have it. Those are our two partial derivatives given z is defined implicitly. So it's not an explicit function where I get a value of z. Okay. So here we notice, how do we do this? Well, to be honest, we just plug it in, right? I mean, that's the point of doing it. uh, yeah, I mean, we just plug it in. So here we were able to define these two partials. So we just plug in the values of x, y, z in this case, and then we would get something out of it. So okay, let's try. So now let's evaluate at this specific point. Oh, I just looked at it a while ago and then I forgot it. Okay, so it's negative 1, 1 and 2. Okay, let's start maybe with the first one. So the one with respect to x. I'm just gonna put my formula here. Where was it? Oh, there. Okay. Then I plug in what I know. What do I know? I know negative. I know my x is negative 1, 2. I know my y is 1. Here when I plug in, I like to put like parentheses just to know, okay, I plugged in a number. 2 squared, 1, negative 1, and 1. And this should give me, here's a negative actually. 2 times 2, 4. This is 4, this is 1, this is 5. 4 minus 2, that's 2. And there we have it. So we have a slope. So we have a surface, right? Um, Funny enough, this is our surface. I'm kidding. Oh no, I'm right. Yeah, this is our surface, right? This thing. And you're able to find partial derivatives at this particular point. And one of the slope of the tangent lines at that point is negative 5/2. So let's try to find the other one. This time in terms of y. I mean, with respect to y. And let me plug in my formula. It should be here. There we go. Great. What's funny enough is that the denominator is the same, but then my x, instead of it being x, it's a y. And instead of it being y, it's an x. So that's I don't know, maybe an interesting pattern to look at. Not sure. I don't know. Maybe it will lead to shortcuts. Okay. Uh, so here we just plug in one for y, plug in negative one for x, two for z. So here now I treat z not as a function anymore. Basically, I treat all of them as variables in this case because I just put in numbers. Yeah. Okay. And I have two. Oh, this one's just the same. So this is negative two. This one is one minus two. No, one minus four. So it's negative three. So actually I get a positive value here. Now I have a positive slope at 3/2. Right? That's interesting. Okay. Let me do some exercises from, well, obviously from my homework. I'm gonna try and tackle some of these problems. And I hope, okay, let's see. Let's see. Um, 14.3. Okay, and let's do it. Okay. Uh, where was I? Oh, um, okay, it's a couple of them. Oh, there we go. We have some implicit differentiation stuff that we can try. Yeah, I'm gonna go out of order here. Yeah, because I just wanna, yeah, let's break down some of the homework that we already did. Okay, so I'm gonna go out of order here. So this is, what is this? Okay. So let's do, actually there are only two. Yeah. Okay, let me do two exercises here, and then we should be good. So here we're being asked to use implicit differentiation to find my partial of z with respect to x and with respect to y. Okay. And we're given this, well, formula, I guess. We're given this equation. Okay, that's a z. Okay, so let's do it. So first we find my partial of z. So here we use implicit differentiation, right? I mean, they kind of said it already, so I'm just gonna go for it. Here we treat y as a number, and we treat x as a variable. So let's do that. X squared is what? Well, that's 2x. 2y squared, that's a 0, because both of them are numbers. 5z squared, well, we can, okay, let's do this. This is 10z, and then my partial with respect to x. 2 is just a 0, right? Okay, let me put some highlights here. I'm gonna say find my partial with respect to x. Okay, and then what happens here? Well, now I isolate my partial, basically. Negative 2x, right? I can divide it in this case, so I can say, oh, negative 2x over 10z. Well, here I could just say negative x over 5z, right? Then that would be my answer. So surprisingly, I don't have anything in terms of y. And that makes sense, right? Well, because I treat y as a number here. So of course I wouldn't get anything for y. Okay, so here I have negative x over 5z. Let me see if I got that. If I didn't, then I think I got it though. Okay, got it. And then the next one, now let's do another. Let's separate the tasks here. So another thing, or at least my tip on doing math, is that you want to separate and label what you're doing because you might get bogged down by all of the equations you're writing. Okay, so here we treat x as a constant, right? And we treat y as a variable, and we treat z as a function. So x here is a constant. So x squared is just 0. 2y squared is 4y. 5z squared is the same as the one we did previously, but this time with respect to y. Derivative of 2 is 0. Okay. And then we again isolate negative 4y. And there we go. We have our answer. Negative 4y over 10z. I could just divide all sides by 2. I get 2y over 5z. And there we have it, right? This is negative 2y over 5. Nice. And we do it again. So number 14 tells us, or number 13 rather. So here again, we use, so we're gonna copy. Okay. And let me do that. Okay, so what is this? Uh, Let's look at our function here. This is e to the 7th over z. I swear, my z looks like a 2. I might just do some, yeah. You know what? The next time I'm going to do a z, I'm going to put a line just to make sure it's a z. Okay. There. So I'm going to put a line just to make sure it's a z. Z over dx. Oh, I want to find that. My bad. Okay, so how do I do this? Well, again, I differentiate both sides, right? So first I find this, my partial with respect to x. So what's the derivative of e to the 7z? What's that? Well, if I do that, well, I should get this, the same thing, times its chain rule. And let me continue. Well, now this is what? 7. Well, we do nothing to the 7. But here we do 7, and then we take our partial, like that. Right? And then here we do it with respect to x. So that part is just basically, well, we can put it here up front. So 7e to the 7z times my partial. And then here's the fun part. X, y, z. What is this? Well, here x is a variable, y is a constant. So I'm going to put my y in front. And I have my x, z here. So that's something I would do. And then maybe I do a product rule. Then there we go. And then what is this? Well, this is a 0. This is canceled out. Because it's just everything here is 0. If we take the derivative of a number, it's 0. Here, on the other hand, we have another partial derivative that we have another product rule that we need to go over. Right? Now here was this. Well, this is just z. What is this? This is x, and it's partial. And then I have my y here. And so what does that mean? Well, I have y times this thing. Right? And so from there, well, we can already tell. Let me shove it in. There we go. And we could actually, let's simplify it a bit. So here we have y. I like doing this. X, y. And there we go. I would swap it with this because I don't know. I just prefer it. I prefer it like this. But honestly, we don't need to. This is totally a preference. There we go. And now we isolate our partial. So we have 7 e to the 7 z, my partial, minus xy. There we go. So I put all of the partials in one side. Just cancel them. Or I factor it out, I mean. I just realized I have a y here. Anyway. And from there, we have this thing. And there we have it. Right? Okay, let me try 7 to the z minus x. I think yeah, this one's yeah. Okay, looks right. Based on how I solved it, one way to find out is to try it. Okay, got it. Nice. And then let's do the other one. And that's gonna be it for this video because I don't want it to be too long. Here we're doing it with respect to y, so not with respect to x. So here we treat x as a constant. Okay, so e to the 7z, well, that's the same, right? So here we just say 7. We take our partial, but this time with respect to y. That's the only difference. And then x, y, z. Oh, shoot, what is that? Here we treat x as a constant. And so we're basically left with, okay, let's divide it into these parts. And then we do a product rule. And then I say, okay, well, this is just 0, so it cancels out. This is x number. This is y. And then we do another product rule here again. Right? And then here we see this is a 1. So this is just z. We add, this is y. And then this is partial. And there we have it. And we have an x here. Right? It's basically all of that. And then from there we have x, z. We have that. I can put this. Yeah, I can put this here. There we go. Okay. And then after that, well, again, I do my isolating. Yeah, so again, really in math, or at least in academics, you just have to remember the pattern or find a pattern, recognize that pattern, and exploit it. That's really all it is. And once you get it, you're done. There we go. And I'm pretty sure I have the same denominator. Yeah, the only difference is my numerator. So that's interesting. Is that pattern? Yeah, obviously it is, because it happened twice. So here it's just my denominator stays the same, and my numerator just changes into what it is respected to. So if it's respected to, well, it changes into what's constant. I just realized. So if it's with respect to x, well, it becomes y, or the opposite, right? And then here, instead of it being y, now it's an x. I don't know, is there a pattern there? I think there is, because that happened like twice now. So I hope you guys can maybe, I don't know. It's something. I would say it's something. Okay, that's all for today, or at least for this video, because I don't want it to be too long. I hope you guys enjoyed. I hope you guys learned. Or if you guys took calculus 1, I hope this was a nice review on implicit differentiation, which is again one of those derivative techniques for finding derivatives, obviously. But here we're just doing it for partial derivatives. So yeah, I hope you guys enjoyed, and I'll see you all in the next one.